Okay, welcome back for those who are back. And as I said, this part can also be seen on its own as an introduction to NumPy. So if you are familiar with Python as a language, but you've never seen NumPy before, you can also just watch this part 3 and it should be self-contained. So as I started off at the very beginning, Python is a general purpose programming language. It was actually originally most successful as a language for web development, for developing complicated websites. And unlike, say, R or MATLAB or nowadays Julia, it's not specifically designed for numerics or for any type of scientific computing. Instead, it's designed. It uses external packages to get that functionality. And so in that context, there's a package called NumPy. I've also heard it pronounced Numpy, but I think it stands for numeric Python. So NumPy, I think, is the more standard pronunciation. And so the NumPy package is the quasi-standard, so not built into the language, but almost everyone uses it, package for doing an array of numbers. So this provides just the basic functionality, but then there's there's a whole ecosystem of other packages that are built on top of NumPy that give you all of the machine learning elements, but also computer vision and image processing and signal processing and a whole plethora of different numeric capabilities, statistics as well, obviously. And so NumPy is not officially standard, but in practice it is the basis of all numeric and scientific computation in Python. All right, so but as I said, it's not built in. So the first thing we need to do is we need to import this library. So here, let's switch to the code. So syntax import NumPy as NP. And so in this as NP bit is actually not optional, but it's very, very standard to use this NP abbreviation. And so we import NumPy, and import, it's like include or require, or the other languages use this similar language where you are taking a package that's not part of the language and making it available in this current script, and then we can refer to it as NP, and the basic thing that it gives us is this NP array. So you'll see, actually, maybe here let's even start with the, just print A. Okay, so so A is just this array of numbers. So it's a two-dimensional array, so with rows and columns, and then we can access individual elements using this bracket syntax, like if it was a list, but here we can use multiple indices. So this would be the first row, first element, first row, second element, second row, first element. So this would be, let's see, yeah, so this would be 0, 1, and 2, and this is the basic element. All right, so a fair question at this point is, we've seen lists before, so lists are part of Python, so we can have lists of numbers. So why do we need NumPy? And so there's three reasons, and we'll go over them one by one. So the first reason is that NumPy arrays are designed for doing things with numbers in general. So we have a lot of convenience methods that do numerics. The second reason is efficiency, and this will be an important one. And the third one is expressiveness. But let's go through these one by one. So I'll have this example of A is an array with the numbers 1, 2, 3, and B is a list with the numbers 1, 2, 3. So, so here A, no, sorry, I forgot to run this, as I said. Yep. All right, okay, yeah. So as I said, we have these convenience functions. So mean, the mean value, 3. STD, the standard deviation, the maximum. So these are not so surprising. It's also interesting to see that, so we have, I'm sorry, skip ahead too fast. We can use numeric operations and they work element wise. So if you see A plus 1 will be an array where we add to each element. So add 2, 3, and 4, okay, multiply, and all of the standard numeric operations will work. So you can, and they will work, and we can also do this with multiple arrays. So let's say we have a second array B. So now both B and A are arrays, and we can add them, and they add element wise. A plus B is so 1 plus 1, 2 plus 1, 3 plus 2. And A times B is 1 times 1, 2 times 1, and 2 times 3. So this is why I've been calling them arrays and not vectors, because everything works element wise, and not, so these are not matrix and vectors, or these are not, tensors. These are just multi-dimensional arrays of numbers. We can get these operations. So if we do want to do a matrix vector operations, we can, except we do it not with the multiplication operation, but with this dot function. So np dot does the matrix vector multiplication. So in general, it's not just a vector dot product, it's a tensor multiplication. So if it works, if A is a matrix and B is a vector, then it's a matrix vector multiplication. If both are matrices, it's a matrix multiplication. If both are vectors, then it's the vector dot product. So in more modern versions of Python, there's also this at operator, and the at operator, which was actually introduced specifically for NumPy, does this special type of multiplication. So the matrix, or generally speaking, the tensor multiplication. But this is not the default. So the default operations with arrays are element wise. So this is why I'll always be talking about them as arrays and not as matrices and vectors. All right. So this was the first argument, is that for NumPy can be very convenient. So if you really do have numeric arrays, then it's very convenient to be able to add 1 to all of the elements, to multiply all of them by a certain value, to scale them up, to scale them down. So that's the convenience argument. The next argument is that NumPy arrays can be much more efficient. So let's think about, what's a list in Python? So a list is a object that's then a list of objects. And as I said, lists can have heterogeneous types. And so, if you think about how this is represented in memory, you have some object like this. So that has a little tag saying, hey, I'm a list. And then it has 3 objects. So let's say this is the list 1, 2, 3. The first object has a little tag saying, hey, I'm an integer and I have the value 1. Second object has also a little tag saying I'm an integer, I have the value 2. And the third object has a little tag saying I'm an integer and I have the value 3. And so if you are, for example, trying to compute the sum of this, the code will have to go through each one, check its tag, see if the tag is compatible with doing addition, and then call the appropriate addition function. So when we have a NumPy array, we have something a little bit different. So we have a single tag that says, hey, I'm a NumPy array of integers, and then you have a contiguous block of memory with the numbers 1, 2, 3. And so computers are really, really good at doing this type of handling this type of data. So if you have a block of memory with just numbers and you want to add them up or add them to another block of memory, then computers are really much better at doing this than if they have to do this logic at each step. And so this is going to be very efficient. And the other argument as well is that, so there's a whole world out there of, for example, in the linear algebra world, of libraries that have been written and optimized throughout the decades, and they're written in Fortran or C, and they can accept these blocks of memory. And so if you have them as NumPy arrays, then it's very easy to call into any type of compiled code, including these 50-year-old Fortran blocks of code that are really very, very highly tuned by now. So let's actually just see. And also this is nice because I am going to introduce another concept here. So let's look first at this. Okay, so all right, so A is a list constructed out of the range. So we saw before this range object, there was this weird iterator thing. So we can call list as a constructor. So here basically it looks like we're calling it as a function, and we're converting this into an actual Python list. So now we have here an object that's a list, which contains the integers from 0 up to, but not including 1024. All right. Okay. So this was perhaps all right, and then here I'm going to call this magic command timeIt. And so there's this %sign timeIt. So the %sign indicates that we're actually calling a functionality not of Python, but of the Jupyter notebook itself. And then there's a few of these, and one of them is timeIt, which you give it an expression and it times it. So this is a special, it's called a magic command for Jupyter, and then you give it the Python expression and it's going to run it. And it's kind of a little bit smart about it because it runs it multiple times. And then it's going to tell us how long it took. And while that's thinking about it, all right, oh, here it is. So it took 17 or 16.9 microseconds, and you can see it ran it 100,000 times. And that's not bad. So let's see how we do it when we do it with a NumPy array. So the first thing here, we're calling the aRange function. So it gives us an array that's like a range. So this is, so let's actually just see it. So here actually the display is a little bit better, but it's pretty much the same as the A. So where we have an array from 0, blah, 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 up and to, but not including 1024. So if we time it, right here, it's actually, so it's actually faster. But we've saved 10 microseconds. It's about slightly more than twice as fast. And frankly, for this small arrays, small computations, we could say, who cares about 10 microseconds? It's a factor of 2 is also, if we're including all of this complexity and all of these dependencies in the code to save 10 microseconds, who cares? Right, the problem, let's now do it let's do a slightly larger problem. And so here, 1,000 times larger. So, and we do a slightly more complicated computation. So here we're doing the sum of the squares. And, now, it's not twice as fast. It's from says from 5 to 135. So that's about 70 times faster doing it through the Numpy version. And so as the data sets grow, it starts, and as the operations get more and more complex, it really does start to matter whether you are using the raw Python version and that overhead, or whether you can use the optimized Numpy versions. So this was argument number 2. So Numpy is faster, and the argument number 3 is that Numpy arrays are homogeneous, and so this is a double-edged sword, or a lot of these things actually that we'll talk about now. It's more that they're very sharp swords, so it's very powerful. You can get very fast results, but you can also cut yourself if you're not careful. So in Numpy, you have an array, and every member of the array has the same type, and this is defined when you create the array. So we've been doing things like this: a equals np array of square brackets blah blah blah, and here we did not specify the type. This was implicit, and Numpy just kind of tries to figure it out. And in this case, we can also look up, and here a little bit of syntax: a.dtype looks up the dtype element in A, and dtype is short for data type, and this is an int 64, so it's a 64-bit integer. If we give it floating point numbers, it will give us floating point, or we can also be explicit, and so when we construct it, we can also call the dtype, give it a dtype argument, and explicitly say, I want this to be a 64-bit float. And so to some extent, this is why it's so fast, but it's also kind of nice that you can be more expressive. So if you have a NumPy array that's supposed to represent a matrix of numbers, and this is very common in all across the sciences, it's nice that this really is an array of numbers and not a generic list that can have strings and numbers, and then mix in other lists and have pointers to itself, and so it's nice to be able to say, no, this really is just an array of numbers, and all of the code can assume that it has it just has numbers. Okay, so I showed you this int 64, but there's other data types. So here, int 8, int 16, int 32, and int 64. So these are 8, 16, 32, and 64-bit integers. There's the uint, so that stands for unsigned. So that would mean that that only non-negative integers, and the floating point variance. There's also a Boolean, and we'll see that actually come up in a second. So now, unlike with the standard Python integers, we can have over and under flow. So here, for example, we have an 1, 2, 3 as an unsigned 8-bit integer. If we subtract the 10 from each, this would come to -9, and -9 reinterpreted as an 8-bit integer is the value 247. And so this is a bit the trade-off, where in return for being much faster at operating, we have to take into account that we have limits in what kind of range we can represent. Okay, so the other things, let's talk about some other things that are very useful. So we can often use this reduce operation across access. So here's a 2-dimensional array, and we've seen this max method before, but we can give it an argument and say we want max, and actually can even be explicit. Say x is 0. So this means that we want to compress the axis 0. So we do it across the rows. Sorry, yes. So that here, the first row, the maximum element is 2. The second row, the maximum element is 4. The third row, the maximum element is 3. This may seem a bit artificial, but so for example, a common way to represent data is that you have your rows could be your instances of objects, and each column is a feature of each object. And then, for example, you might want to ask what's the maximum value of each feature, and this would be this exact operation. Or if your data is arranged the other way around, then you can say that using axis 1. So, and remember, if you don't give it any arguments, then it's just the maximum value overall. So this applies to max. We saw min. So all of these operations, they also take this axis argument. So if we say min axis 0, so this would be, sorry. All right. Okay. Slicing. All right. So this is, again, let's look at our array, two-dimensional array. Let's look at the shape. So the shape is, again, is a tuple. A tuple is kind of like a list, but we write it with parentheses instead of the square brackets. And a tuple is exactly like a list, except that you cannot change its values. So it's kind of like an immutable list. And so here, this is a two-dimensional array. So we have 4 times 3. Okay, and we've seen how we can access individual elements with the square brackets, and then we give it the first index, the second index. But we can also just get if we just give it 1, so we've gotten a slice, so we've gotten a row, and now we've gotten the shape, instead of being 4, 3, is just 3 elements. And okay, and we can get the second row using the same syntax. And here's a little bit of funny syntax, but so square brackets, colon, comma 2. So this means we want all of the elements where the indices have something, and then a 2. So this would mean 0, 2, 1, 2, 2, 2, 3, 2. So if you think about it, now instead of selecting rows, we are selecting columns. So this is the third column, the column with index 2. All right, so here's the important part. Slices share memory. So a slice is a view into another array. All right, so let's just remind ourselves what the array looks like. All right, here we built a slice looking at the first row. We use the slice to change the element at position 0. And so this will change the element in A. Okay, so remember this very sharp sword. So it's very nice because sometimes it's very useful. It's obviously very fast because we are not building a copy. But it can easily lead you astray. So for example, this also implies that if we have a function, so for example here, that takes an array, when we pass it an argument, effectively we are passing it by reference. So the function is changing the values inside A. So if that's not what you want, you can always make a copy. So there's this copy method, spelled copy, which makes a full copy of the array. And so here you can see, or you can also do a copy of a slice. So here a square brackets 0, this would be a slice into A, but then we copy the slice, which makes it into an independent array. Or actually let me show you a little bit more complicated. All right, so here 0 colon 10. So this would be the slice that goes from 0 up to, but not including 10. So in terms of indices, so this would be the first 10 elements. And so then we can make a copy, and now we can see that the copies operate independently. If we do not make a copy, then changing one changes the other one, right? So copy can obviously take a little bit of time, especially if the arrays are very large, but you know, then you are safe. All right, so logical arrays. So we can do this operation. So for example, a greater than 0 on an array, and then as many other things, it works element wise. So it's going to check, is this value greater than 0? Is this value greater than 0? Is this value greater than 0? And returns an array of booleans. So false, false, true, true. And one of the nice things about it is that we can do numeric operations with these booleans. So here I'm going to give you a couple of seconds to try to wrap your mind around this. So this is the AND operation for boolean. So true and true is true, anything else is false. All right, this returns 0.25, so 1/4. All right, so what does this mean? So when you do numeric operations with booleans, you are basically false is 0, true is 1. And if you think about it logically, this is all of the elements that are between 0 and 3, and the mean, so that's a fraction. So doing the mean of an array of booleans gives you the fraction. Often it's also useful to do the sum, which gives you the count. So how many elements are true. So this is really very useful often. So you know, maybe it takes a bit of getting used to it, to treating booleans as numbers, but treating them as zeros and ones. Once you get used to it, it really is very logical and very intuitive. Once you do build that intuition. Okay, we can also use the Boolean arrays in other ways. So for example, we can use them for indexing. So let's do an operation on all of the positions that fulfill this condition and set it to 0. Or this is another way of doing the exact same operation, it's a different operation, but getting the same result, where we multiply something by an array of booleans. And again, if you multiply by 1, you don't change the values. If you multiply by false, you turn it into 0. Again, maybe strange at the beginning, but very intuitive once you get used to it. All right, we're almost at the end. So I'm just going to show some helper functions. So there's a function called zeros, builds an array of zeros with the shape that you give it, 10 by 10. An array of ones, same, except you get ones. Zeros like, and there's also ones like, give you an array of zeros with the same shape and type as its argument. And there's a lot of other ones. I'll show you the NumPy documentation at the very end. Okay, last thing I want to talk about is NumPy. Matplotlib. So Matplotlib, again, not part of the standard library, but very, very actively developed, widely used. And it's maybe as the name says, it does plots. It's a library for plotting. All right, so here again we have to import it. Here I'm importing matplotlib.pyplot splt. I'm also importing this style function or this style submodule and saying that I only need to use the default style. And then here x equals linspace. Also a new function, linspace gives me an array from -4 to 4 with 1,000 elements linearly spaced. There's also log space, which will give me 1,000 elements logarithmically spaced. And then I'm plotting x to x squared times cosine of x squared. And so if this works correctly, you should see a plot like this. Right. If you don't see the plot, you should try using this matplotlib inline magic command and try running it again. So this used to be mandatory in earlier versions of Jupyter Matplotlib. Now it's done by default, but if for some reason it's not showing up for you, ask for the plots to be done inline. Inline means that they show up within the notebook itself. Okay, so here we go. All right. Finally, very last thing. So this almost looks like magic. We can do these widgets inside the notebooks. And so here we're going to import IPy widgets, import interact, and here, all right, let me first just delete this. Okay, so here we have a function. That's actually 3. Here we have a function that when we call it with an argument, it makes a plot that depends on that argument, right? So we call it with 3 and it plots it like this. Okay, and then if we add this interact, so in here this is an @ interact, and then we say the power equals 1,10, then it's going to generate this little thing here, and then we can just change it, and every time we change it, it calls the function and it gives us a new plot. And you can do more complicated interactions, but 95% of the time you just want to use the default ones. So here's, so if you give it you can get booleans, get checkboxes, integers or floats, you get this slider, and if you give it a dictionary, you get these sort of Dropbox. So you can. All right. So for me, actually, this is for me the thing I sometimes use about notebooks. So I actually use notebooks a lot for teaching, but I don't particularly use them for my own development. And so there's this very well-known talk on I don't like notebooks by Joel Gross, and so there's a lot of disadvantages and a lot of advantages. I think for teaching it's quite nice because I was able to have this text blocks within the code, and so often for communication it's quite nice. But there's alternatives, so you can obviously just use a text editor like VI or Emacs or something, or you can use a type of IDE. So here one that is very widely used within the Python world is Spider. So here's and so this looks, so here's my code, and what's actually kind of nice about this one is that, so here I've just run it now. What's nice about this one is that it integrates also with other things. So here I've defined these arrays, and so here in this variable explorer I can see, here's the values of the arrays, and even get some graphical input about what my data looks like. So this is also a perfectly valid option. All of the Python stuff that we learned will work perfectly well, whether you're using the Jupyter Notebook, whether you're using an IDE like Spider, whether you're using Emacs or Vim, or there's IPython on the shell. So all of these things will work correctly. So maybe just as a last thing I want to show, I'll give you a couple of links. Oops, sorry. Yep. Okay, give you a couple of links to the documentation. So NumPy documentation, fairly complete nowadays. I mean, they've made an incredible effort to make sure that everything is documented, every function. There's so very nice. If you go to the main page, so the NumPy, you can see a lot of there's a pretty extensive also for Matplotlib as well, and Python itself. So for Matplotlib also have a lot of examples of all of pretty cool plots that you can do with the code behind them. And so that's what I had for today. And so for now, let me know if you have any questions. Now it's the Q&A session. Thank you.